Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson, and I think we're going to talk today, Fred, about, or if there's a resource document for the physics of failure of electronic componentry. Is that right?
That's right. Daniel wrote a couple days ago, well, actually a little longer than that, because I've been needing to talk to you about this for a while. Specifically, he says, do you know of any handbooks or databases that are useful references for physics of failure models? And specifically interested in electronic components and PCBAs. And I replied to him back then, as all of us typically do, as we get back to any question we get. And it was CALS has published dozens and dozens, if not hundreds of papers and probably a couple of books that include all kinds of models for electronic components and solder joints and everything else involved with it. And DFR Solutions, now part of ANSYS, it has also published a bunch of that kind of stuff. So I know that there are two models out there. Those two groups have created physics of failure models specifically for electronics and circuit boards. But you got to pay a lot to get them, and it doesn't really give you the models directly. But there's a lot of literature out there. But I don't know, other than those two groups, there used to be a system called WARP that was a database and said, oh, I've got this stainless steel 504 or whatever the number might be, and it would do a model of this as this is how it fails, or I have tin, how does this work, and so on. And it had a lot of, there were hundreds and hundreds of technical papers listed. They weren't available through it. They were summarized, and you could then find the title for the topic you want, but they're not, it's not online anymore. I'm not getting any response from that program anymore. So do you know of any that I may have missed?
No, I don't. But also, I mean, to be fair, it's the whole idea of having a definitive list of physics of failure model for PCBs and everything else, it's a challenging thing to aspire to. With like recent challenges, as you know, include the introduction of lead-free solder and a few other things. Why that's important is the state of the art is always changing, and you do have some relatively good university or academic efforts in that regard, trying to understand how emerging techniques and emerging materials can change. To the extent that the attractiveness of trying to summarize electronic component physics of failure modes and models in a single document is probably low.
Yeah, the WARP database was the closest. It had hundreds and hundreds of papers, but it wasn't focused on electronics. It was more materials like metals and polymers. But I mean, outside of a technical library, right, and doing searches for whatever it is you're interested in. And I know Peck and crew have written a couple of books on it that have, dozens and dozens of models outlined in their books. And Zach, I think it's 4 something. I don't remember the number of it, but it's been around for now 20, 25 years, and it's got some reasonable models out there. But it's one of the things that intimidated me and let me back up a little bit. A physics of failure model has many definitions I've found across the industry. Sometimes it's like an empirical study that said I looked at 20 different studies and I drew a common line through it and just empirically fit this curve to it. And that's now Black's law, or, somebody else's who gets it named way back when. That doesn't typically, it's used for accelerated testing. It's used for modeling for all kinds of cool stuff, but it's related to usually a specific failure mechanism in a specific type of system, which are parts of a physics of failure model. What I see the university folks doing is they'll say, all right, we have these kinds of loads and these kinds of stresses and this distribution of cycling, and then we have all these different things, and then we go into detail how about a crack initiates, and then there's a different mechanism that propagates it, and it's different stresses are applied. And in order to populate the model, you need the material properties, the manufacturing properties. You need all of these detailed. I tried filling it out once for one multi-layer ceramic capacitor, and it was 35 different parameters I needed to have information for. And some of them are proprietary to the
Right.
vendor. And I like, okay, this is not helpful. So I think there's a wide range
Yeah.
of models that get lumped
Yeah.
under, in some cases, physics of failure models, where you're focusing on how does a mechanism initiate and propagate.
There is, I remember a model for creep, the progression of creep, which I think had, what did you say, 35 parameters for yours? This one didn't
Mm-hmm.
have 35, but I think it was 12.
Mm-hmm.
And it was actually a lot more useful because those 12 parameters were, shall I say, attainable. Like they were based on the properties of steel, the
Right. You can look
strain
that up.
coefficient, yield strength, all those sorts of things. So it was quite involved, but potentially quite useful if you had the challenges of getting those parameters were not insurmountable. Still requires substantial effort, but not insurmountable. There's no IP or proprietary barriers the way you're describing.
Mm-hmm.
Now, I also, I suppose we should go. So that's what I'd call a physics of failure model. And not only is there a detailed model of the failure mechanism itself, but the uncertainty in the outputs is also part of the physics of failure model. So that any variation in, for example, defect size or distribution, or that then generated the uncertainty or range of times to, well, creep rates
Mm-hmm.
with this very high level model. At the other end of the spectrum, a model which is entirely not physics of failure is where you gather times to failure for a particular component and then find your favorite probability density curve that fits that. That's the opposite.
Right.
And there's everything in between. So you could argue that, hey, if I know that the log normal distribution fits this failure mechanism I'm studying, so whilst I'm simply doing a reliability life test to gather times to failure for this component, because I know it's failing due to fatigue, I'm going to use a log normal distribution to model its time to failure. You could argue that's got a dash of physics of failure in that model because
Right.
you're using an understanding of the failure mechanism to help you work out what your model should be. You could also go one step further and say, well, if we're doing accelerated live testing for a failure mechanism we know is a chemical reaction, then the Arrhenius model would then help you define the characteristic life, but you'd still usually have some sort of bell curve or log normal distribution describe the variation
Mm-hmm.
each side. So you have a combination of physics of failure and stochastic or purely random model. And so it's not a binary bucket. You do have models which are entirely stochastical, just bell curve like, and models which are entirely physics of failure. But there is a substantial continuum where you might have a dash of one or the other, or a healthy combination of both moving forward. So even saying, please give me a physics of failure model is not of itself generating a very non-grey boundary between what people want and what people don't want.
Well, one of the things I didn't respond with in my reply to him, and it just dawned on me, you and I usually talk about it, is, well, what do you need them for? You
That's
know?
the next thing, yeah.
Yeah. And so that's when you're describing is there's this quote, I want to ascribe it to George Box, but I'm not really sure, is like all models are wrong and some are useful.
Yeah.
And then there's a corollary to it, and I don't think it's from George. It may well be, but it was, The model needs to be as complex as it needs to be useful. Not anymore. And so some of the academic stuff I've run into is overly complex to the point where I can't even guess at what these numbers are for the interstitial bonding motions, of the ceramic that's used in this obscure type process. And I'm like, okay. Or if my sintering temperature has a variation of more than 7 Celsius, then then you have to account for that. I'm like, how in the world would I ever know that? you know,
Right.
you know, you had the luxury. Yeah. So if you come back to like the 12 parameters or to can you observe it and measure it, then you can do something with it.
Now, it does go back to one of our constant criticisms of academia more broadly is that you get rewarded for publications, and publications tend to prioritize things that are novel and new, not just things that are necessarily useful and applicable. So we often have these increasingly complex and technically sophisticated models to describe an decrease or vanishingly small portion of real world applications. But yeah, so going back to what we want, what does this guy need this stuff for? Again, as a rule, you want to make the thing reliable before you measure how reliable it is. I dare say I've worked on LiDAR, for example, where there is
Mhm.
one single electronic component that is a laser light emitting diode, which is so central to everything that yeah, physics of failure model for that single component is actually quite helpful and useful, or maybe not even just that, mandatory or necessary to get on top of reliability challenges. So if it's just like a general list of models in order to help improve reliability analysis, yeah, you want to only apply a really high-end physics of failure model to a really overwhelmingly dominant set of failure mechanisms, which is usually quite rare in the field of electronic componentry. A lot of failures come down to silly or stupid vibrations associated with shock forces in the solder joints when the things get dropped, which
Yeah.
HALT can really help you identify and mitigate.
Yeah, and Kirk and I were talking about it the other day, is that there's so many things that, the academics and lots of reliability engineers, we tend to look at, well, when's the end of life? Will this last for 20 years? And we miss the really painful failures of it was damaged in transit, or it wasn't assembled correctly, or it had missing parts, or the solder joints were insufficient, or cold solder joints, or the boards weren't correctly laminated or heated, or the components weren't manufactured correctly. And I
Or
have all
moisture
these
got in there.
latent, yeah, and moisture and all these latent defects that can get into it that really do wreak havoc with a lot of electronics. Yet, if we assume that goes away, we were kind of hoping that it's not significant at number. And so many reliability engineers focus on the 20-year problem and ignore a major problem in the first 6 months. But that's an aside. And there are models for a lot of that stuff, but I think back to your point, it's a whole lot easier getting a couple of prototypes and doing HALT. And you've got a laundry list now of things you need to go fix. Just go fix them. And I think like the LiDAR LED, the laser part of it, is there's all kinds of facets to that, power and alignment and frequencies and all these things that are essential for that system to work. And having solid models will help you then in the design process to know if you got a robust product or not, and then do some testing and compare it to the model to verify it. But it's the use now. To be fair to Daniel, he may be looking at writing a book on this subject or something like that. Or
Right.
like what I would always interested in is, well, what is available? Maybe there's something out there that I can skip this accelerated test and just use the model because it's a perfect fit. It's being aware of what's out there might be part of the question.
Yeah, and I think that there's also scenarios where where you need a physics of failure understanding, but you don't need to have it. You just need to know, like, if you're doing accelerated live testing, if it's a chemical reaction, try the Arrhenius model.
Yeah, but then you still need the activation energy, and you need to understand that chemical relationship well enough. I usually just go find a chemist. They're always happy to go do chemistry things to figure out activation energies.
You don't
But
always
isn't,
need to, though.
well, no, if you set up 3, 4 sets of temperature stresses and you can back calculate it out if
Right.
everything's perfect.
But that's an option. You can get it. But if you have that chemist you're talking about, usually has to be intimately involved with that component in that context with that material.
Oh, yeah.
The sort of Google research activation energies I've found are,
Oh, less than helpful.
yeah.
Yeah. No, I looked up one a couple weeks ago and it was, well, it's typically in a range between zero point 0.2 electron volts and 1.2 electron volts. I says, yeah, that's generally true of all chemical reactions.
Yep.
So that's not helpful.
Well, actually, it can be. I mean, if you can take the edge cases for many chemical reactions and say, okay, with the lowest activation energy, i.e., the fastest chemical reaction, we are still meeting our specifications, or that's a good thing.
Yeah, it's good. Yeah, yeah. But I've never run into that circumstance. I've used that technique in all kinds of circumstances. Does it really matter? Do I care what this value is? Let me try the high and low of a nominal of a range that's in the literature, and it doesn't change the decision. All right, pick a number, move on. It doesn't matter.
Right.
That it's expedient, and the academics I've worked with and the true what do you call it, the ponderous professor types,
That's right. Yeah.
they would just, no way, you need this activation energy to 3 decimal points or more and proof of it and everything else. It doesn't matter, it's irrelevant. But other times, if you don't do that sensitivity type analysis, you may miss something that is crucial. You do need it to 3 decimal points. And because it's so influential, which activation energy in general is in those equations, that yeah, you gotta pay attention to it. But I think the idea of there's a range out there, and it goes back to, I think about a year ago, somebody asked about a failure mechanism database, and I said, well, there's a lot of literature out there. And I ran it past a handful of people, and I think, like you and everybody else, said, well, that would be a big project to
Yeah.
catalog and define. And is there a model for, every known failure mechanism?
And let AI help you too. AI is very good at doing literature reviews for your applications.
Yeah, Kirk sent me a stack once because he knew I had library access at Maryland, and he used AI for a paper where he's working on, and it was half, truly 50% of the 10 references AI recommended were total fiction.
Oh,
They had great titles. He was really hoping there would be a real paper, and great abstracts. He thought they'd be just perfect, but he wanted to read the paper and make sure it was real. So we checked, and half were not at all. So I have a huge grain of salt when it comes to AI telling me where's a good reference.
oh, I definitely agree that you got to check the stuff. But by the same token, AI 3 months ago is not AI today, and its ability to rapidly research is quite astounding when you know how to use it.
Okay.
And different platforms are very different too, very
Oh
different.
yeah, yeah. No, I get that. So I might, next time I want to research something like every known physics of failure model, I'll send you a note and you can use your system. But there was complete aside, as Kirk and I talked about it. I think it was the episode a week or 2 weeks ago, and the way the scheduling is going to be out, that it was AI names the best reliability engineer or something like that. And what Kirk and I did is we both put in the prompt, who is the best reliability engineering consultant in the world?
Who to
And
come up with?
well, mine came up with me. I was
Oh,
very pleased with that. That was absolutely wonderful. And it had Ricky Smith and a handful of other people I recognized. And I thought, oh, cool, I'm in there. And Kirk ran it, and it didn't have me. It did have Ricky Smith, but then it went down and a little bit later saying, oh, Kirk was an expert in in Halt application. And so we were both very pleasantly surprised that we were named in our own query. So then we tried it incognito, and neither one of us were in our results.
Oh, there you go.
Yeah. So it might give you answers it thinks you want to hear. So if you are looking desperately for a physics of failure model for XYZ system, it may point you in the right direction or not. But like you said, you got to check. You need the paper, you need the document, you need the resource.
Absolutely. I mean, look, I shared my analogy with you, but when I teach how to use AI, you got to treat it like the drunk Sheldon Cooper from Big Bang Theory,
Very
where
smart, but not practical.
right, well, hyper literal can take certain things very, very seriously that you wouldn't think would need to be taken seriously. Can also trivialize things that you thought needed to be taken very seriously, and it doesn't. Um, it needs to be constantly reminded of what it is you're asking. It
Mm-hmm.
will dedicate this roughly the same amount of effort for your prompt, no matter how big or small. So if you ask it to do an analysis on an entire system, it will dedicate the same amount of effort into the same question, but for a small component of that analysis.
Yeah.
So the granularity or the resolution of the results are roughly proportional to the scope of the question you're asking. All those little nuances become apparent. And also, when you're writing prompts, there's all like I've been writing, creating AI prompts for me as in particular. You've got to have, or I use Word documents or documents containing the text for the prompts, and so some of my prompts are 20 pages long
Wow.
to where you actually teach or show AI. I want you to think of this first, then think of this. Of the things you thought from the previous two steps, move these over here. If you find, you go
Mm-hmm.
through it like that. And then at the end, you have a final quality check. And you say, if you've done this, then you need to go back and think again. So you have all these typical, dare I say it, AI failure modes. And one of those would be confirm, all the references you put out, confirm that they actually exist. If there's any fictitious ones, you need to go back and start again.
Yeah.
And when it goes back and starts again, it remembers that it messed that up last time and tries to take active steps to ensure that doesn't happen again. And so I'm very cautious of these master classes in AI that are starting to emerge right now, where you have these professor-like people who are purveying a sort of level of AI knowledge as if they've been studying it for the last 50 years.
The
Notwithstanding AI
ponderous
came out
professors back out there.
right, even though AI came out 5 minutes ago and it's changing every 30 seconds. There is an art to it, but yeah, I'm just very cautious of people who either use, say, AI. I'm an expert at AI versus people who say, well, it doesn't work because I asked it a single line question and it did something weird.
Yeah.
You do. There is a middle ground to be had.
Oh, I agree. I totally agree. I'm going to get back to the physics of failure. So, I mean, if you
Oh, yeah,
go, if you get into that realm and you ask AI for it, think it through what exactly you're asking, what kind of results you're getting, verify it. It also, I mean, really depends on what are you trying to do. If it's simply how many physics of failure models are there, um, which would be an interesting trivia question for the moment. Um,
it's a lot.
a lot. But it's if you really just need models or you want to be aware of what kinds of models are available for the technology you're using, go to the library, get the literature search. Almost every material we use, unless your team just invented it, is usually fairly well documented. Not everything is, but a lot of materials and a lot of components. I remember I don't think it exists anymore. It was called CARTS, capacitors and resistor technology symposium, but they covered all electronic components, and their um, uh, set of papers go into just loads and loads of how things fail and what kind of models exist for them and all kinds of stuff. But it's older literature, so your mileage may vary. If you're working on a system that has technologically advanced, let me put it that way, it may have inherently avoided or designed out the mechanisms that were relevant 30 years ago. So
Right.
models age, and so there literature searches for the authors that come out of CALS or out of DFR Solutions is a great start for electronics components. The one database I knew existed out, I had a good number of them, is no longer available. And it's another nudge to get a similar type system and all the caveats up on Ascendo is explain failure mechanisms and what kind of models exist and where they apply. So, Chris, you've got an extra day or two every day to write that all up?
Not even a little bit. No.
Oh, okay.
I mean, if someone wants to pay in advance, then yes, I have all the time in the world.
Yeah. No, it would be a big project, but I think it's a good question. I want to understand how things fail and what things play, impinge on that and affect the rate of failure. It's an excellent question. Yet I don't have a real satisfactory answer saying, oh yeah, go to physicsoffailure.com and you'll have every model you ever known to man,
But yeah, again, it comes down to the decision. Like an example question that can be answered by physics of failure is, which material do I use?
Yeah, or does humidity affect the rate of failure?
Yeah.
Then you can do design decisions. You can make decisions based on that. Vendor A, vendor B, or this material, that material, or this protection or not.
So yeah, or it could be just, which accelerated life model should I look at as a candidate one first? It's all, what's the question or what's the decision we're trying to make here? And then most other, you save a lot of time and effort once you narrow down the scope of your decision.
That's right. Yeah. Unlike when I get a book and scroll through it and then I find a reference and I go find that and I find its references and I go track down that and then I'm off 15 steps away from whatever it was I was originally looking for. But that's just me. So anyway, if anybody knows of a really decent reference source or a good collection or a good book that gives you the basics or all the caveats and all that good stuff that's practical that we can actually use, that would be great to know about. There may well be something out there. Obviously, we don't know everything. I think the more I know, the less I understand. Was it the more I understand, the less I know? Is that the way that works?
I think. I can't remember the exact quote, but I know what it means and I feel it every day.
Yeah, there you go. So if you got an idea or a question like this or on other topics in reliability engineering, let us know. Head over to accendoreliability.com/go/SOR. A couple of ways to get in touch with us. And then Chris and I and the other hosts of the show are available through LinkedIn and our About pages. And like Daniel found out, we do respond. We try to get you an answer and then we'll follow up if we learn something more and talking through it with one of the episodes. So it's a great way to get those questions answered by some folks that have a bit of experience. Well, Chris, you're not that old yet, so you got to keep working at it. But yeah, do fire away your questions. We'd love to incorporate that into the show and help you out in the short term too. So with that, Chris, I think we'll wrap this one up.
No worries. Just start Googling and AIing our way today.
All right. Talk to you later, Chris. Let me know when you get back from your search.
Cheers, Fred.
All right, cheers. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.